So let's start with the presentation and a few words about the IEEE Computer Society in the Israeli chapters. So we are honored to have Jesus Labauda to give the talk. Actually, this is the first talk. By the way, can you see the presentation, my presentation?
Yes, we can see that.
Okay. So the charter was not active for some time until recently. Dr. Leah Goldin led all the activities, and we thank her for the great job that she did for long time. I hope that maybe next time in one of the future talks we can have it with us as well. Right now, myself, I'm Avi Mendelssohn, and Freddie Gabay are they ask us to lead it, and we try to do the best. And this is the first webinar that we are planning. So in the future, we want to have a monthly webinar. We want to have hackathons. We want to have a local conference. We are thinking about youth activities, and if you have more ideas or if you want to share it with us, please send us emails, and we'll try to see what we can do. We want to start a youth thing, even though during the COVID time it is quite complicated. So the agenda for today. We'll start with the talk of Professor Jesus Labauda, which is a very famous computer architect and had a lot of contribution to parallel languages, parallel system. Right now is focusing on machine learning and architecture and future systems. He's one of the leaders of this EPI, which is the European Process Initiative, which is really interesting because so far most of the effort around the RISC-V was around building controllers and small systems, and I think that this is one of the first initiatives, not the first, one of the significant initiatives to try to put RISC-V not just for small system or controller, but to make it a mainframe or a system with huge capabilities. So it will be very interesting to listen to the talk. Together with us, we have Mr. Dan Shekel, which is the representative of, or he was supposed to be Israel, which is the Israeli Office for Collaboration between Israel and the EU. So he will give a short presentation just after this talk about the activity, and we hope that the next meeting will devote the entire meeting to discuss about research collaboration opportunities between the industry and the academic in Israel and the EU. So with that, I will pass the control back to Jesus for his presentation. And one more comment, since this is a webinar, so you don't have the opportunity to open the mics, at least right now. So if you have questions, just raise your hand. And I see that already one did it, and I'll try to answer. And if needed, I'll ask the question or open your mic to ask it. So with that, I'll try to, first of all, I stopped sharing. So I think that right now, just you can show your slides. Yes.
Okay, Avi, you already have one question. Yeah. One raised hand.
Yes.
I see that one raised hand already exists.
I will look at it. I try to see For some reason, I see that somebody raised hand, but I cannot read it. Okay, I suggest that Javier, please start, and I will, in parallel, I will try to handle all the technical issues.
Okay. So thank you, Avi. Thank you for inviting me to give this presentation on as you said, the RISC-V vector for high-end, let's say, for high-performance computing that is being developed in the EPI project. And I will start. I like to start with the typical disclaimer. In my case, there's a point that you will start using the argument that it's better to give, let's say, or leverage age rather than force or than beauty. In my case, I like to say some of these ideas or statements here. I think they are kind of more important than many of these others here. This is the kind of thing I will permeate throughout the whole presentation. I will be talking on the specific processor stuff, but I will be trying to give a little bit the kind of the motivation, the thoughts, the vision, why we think, or how I personally believe that it's an interesting kind of architecture, an interesting kind of development. And thank you, for saying I'm an good architect. I don't know whether I'm an architect, and I don't know. I moved from architecture to the software, to the dark side of, and I'll try to give a little bit of a kind of a holistic view. But just to say, I mean, a lot of it is personal opinions, and it's really totally open for discussion if people want to. And as such, I will start with two sections, 2 bullets on this kind of generic kind of philosophies or visions, and then when I'll enter into a little bit more of detail or the architecture itself, and then of the infrastructure that we have to do software development and actually verification of and development of the system. So on this vision on HPC is a kind of classical message, I think I'm trying to say, but I do believe that we are, or we should be, probably, in a change of ages from what has been the latency age. And we have been in architecture always worried about latency and minimizing the number of cycles that you had to get one data, or minimizing the MPI communication latency from one processor to another. So we have been in this latency dominated age. And I would like to see us change or move to, in HPC, which were workloads, which are scientific computational workloads, to a situation where we have actually a throughput age, something where we instantiate a lot of work, and it's not really that relevant how much it comes or how fast it comes, but as long as it keeps coming, we are happy. And this is something that I believe happens at all levels of architecture and system software. And in reality, I kind of was trying to push this idea for a long time, a little bit on the software side. But I think the EPI project itself has been for me an opportunity to see how the same concepts, the same vision, the same idea is something that permeates and can be used at the architectural level. Just again to display a little bit what I believe, how I would describe what the last, I don't know, 15 years have been with multicores and what they have done. And essentially they have actually introduced a huge leak in this ISA API level. Now people need to know a lot about the actual architectures of the caches or the private memories or the scratch paths or characteristics of this accelerator or the other. And this is something that is kind of making programmers' life really, really difficult. In a sense, I would say, if you ask what programmers need, I would say hope, okay? Somebody to tell them that they will survive the next generation of machines. And in a sense, I believe that we try to address this situation, okay, which actually in the past has, I think this is the history for HPC, where from small codes we have been kind of evolving towards more and more complex codes, which are actually having even changing shapes of the codes. Let's say porting to GPUs or things like that, just with the idea to adapt to a hardware, but introducing a lot of hardware specificities. And the idea that I would like to stress is that there is hope that we can really go towards a more concise and more elegant description of the algorithms, programs being used to communicate ideas between humans. They happen to be executed by machines. That's nice, that's great. But this try to intention to go towards a more simpler, more elegant way of describing the codes. And part of this way of achieving it, the way we propose it, is by really trying to rebuild this osmotic membrane that, in a sense, ISA was at the time. And we initially tried to propose it at the higher level than ISA, at the runtime level, and we did a lot of work, as you said, on the software side of it, on the task-based programming models for parallel systems. But from a certain point of view, this RISC-V project has been an opportunity to show that also at the ISA level, the vector ISAs gives us an opportunity to raise on one side, raise a little bit the semantic level of this interface, and to reduce the amount of leakage of this interface. And if you have osmotic membranes here, you can convey information from the top to the bottom and vice versa, but try to do it in ways which is not really a massive leakage of information, which would result in applications being huge in terms of code, very specific, a lot of if-defs, a lot of specificities for a given architecture. So this is a little bit a first kind of vision, and which I wanted just to introduce, because I think it influences the kind of thoughts. It's kind of going towards vector and kind to try to raise this semantic layer and try to be more decoupled between layers. There is another topic which I wanted to say a few words, which is about co-design. And well, co-design, some thoughts, some comments or some thoughts I have about co-design. It's too much of a buzzword. It's too much of, I don't know, it's like sex at 15, okay, or everybody talks, but very, I don't know, or it used to be. The thing is too much of a buzzword. If we are, I don't know how many people here is 80, we have about it 81 opinions because I have to. Okay, so it's this kind of situations. I wanted to mention that sometimes is presented as putting one user and one vendor and try to do a machine for a given application, and I think it's certainly not that. It has to do about designing full systems holistically. It's certainly also, from my point of view, not about top-down. It's not about trying to put instructions in the hardware. This is probably too much of an obsession that I believe we often have, and I don't think it is like that. It should be more a more important, more generic, broader kind of concept, and I will elaborate a little bit on this. One other consideration is that in order to do co-design, you really need to do design. And not many people has the opportunity of doing design, certainly not at the low levels. And so I think what this should tell us is that each of us should try to see which are the levels at which we have the opportunity, or we are doing actual development, and try to see that as the destination of the co-design. So how do we design this with a good interaction with the other layers, but not necessarily trying to push things down to the lower hardware level. Another thing I wanted to mention about co-design, which to me is kind of sometimes is confusing. I really don't know what is the boundary. Sometimes we call co-design when it is just co-dimension is do I put 2 gigabytes per core, or I do put 4 gigabytes per core. So it's just choosing out of the opportunity possibilities that the guy who did the design of a given platform gives me, and I have to choose that to adapt them a little bit to my workload. But I think it would be very nice, and it's a very good opportunity, and that's how I see the EPI project, which has given us the opportunity to really do design at this hardware level, at the low level, and really think of what to put at which level, with a kind of a holistic type of objective, type of vision. I mean, I don't know, Newton's equation might not be the truth only, but nothing but the truth. But it's not bad. It has been explaining quite a few things, has let us do a lot of devices and a lot of things. So it is nice. It would be nice if we were able to, along the whole hierarchy, kind of try to use and follow and kind of leverage in the different levels, kind of a homogeneous type of philosophies and theories. So this is what I mean by steered by a vision or steered by actual detail and insight. This is another thing which also, I mean, you have the satellites being sent with new telescopes. I mean, the ability that in other domains have to really measure with precision is something that is very important, but there's kind of it would be nice to, in this co-design, to have a kind of holistic set of principles that I will describe a little bit more later. The ones I think have been influencing the EPI RISC-V vector design. But I would like to see co-design more as a kind of circular way where, given a topic or a problem or an issue, you try to identify which is the level, which is the component at which that problem is better addressed in a more productive and cheaper way. And of course, it's certainly true that this device, I mean, the wheel, such a nice invention, is if there's part of it missing, is really a little bit not behaving totally properly. But in a sense, the EPI processor project has given us this opportunity to really kind of consider holistically all the levels of the architecture. We've been able to work in architecture, in compiler, in operating system, in applications. So it's a nice experience from that point of view. It's a nice experience. It's a huge effort designing a system, and it's something that you have to do. You have to build on. Actually build on everybody's effort, and you have to build on interfaces which are standards and which give you the opportunity to leverage what other people does, and give you the opportunity also to contribute on specific things. Doing the whole thing, everything just alone is really impossible. Okay, and in this sense, for example, RISC-V, we believe has a good opportunity for doing that, for being a standard. It's a standard on which you can contribute. You can push your suggestions and ideas. So it's a good component which enables to do this research far more certainly than closed architectures, and so this is, I think this is an important kind of driving why the project, or why we in the project chose this RISC-V kind of architecture. And before going to the philosophical, or when entering the philosophical things, I mean, you can address exascale with kind of different approaches, a lot of very high level, let's say, multi-threading, very low performance cores, or maybe I should have put the elephants here. But so few devices, very, very powerful, and you can come to combinations. Can be a mess depending on how you organize it. I personally would prefer things like relatively heavyweight kind of devices, maybe with a kind of symbiotic type of relationships with other devices that can complement and can do other functionalities, like to let the main ones concentrate on the throughput. So let me go through the basic principles that I believe influence the design, and I believe are important. And the first one is a balanced hierarchy. So managing 1 million workers in your company by handling all of them synchronized with the same instructions, or by having 10 teams of 100,000, or by having 100 teams of 100 each of those. Or so I certainly believe that really the getting to very large scales will require a more hierarchic kind of distribution of the control structures. And if you look at the way parallelism is expressed and exploited towards exascale, certainly there will be a lot of kind of workflow level parallelism, kind of ensemble type of executions, kind of uncertainty quantifications. There is another level which is also provides a lot of parallelism, or can provide a lot of 10,000 or something like that standard. So, which is MPI, but then in OpenMP, I do believe, and given also the existence and the appeal, the fact that fat nodes are common today, there should be kind of a hierarchical kind of a structure, also supporting very regular shapes of the structure of the parallelism, but also supporting more irregular kind of shapes of the structure of parallelism. And what I do believe is, so each of these levels should provide a certain level of concurrency, probably not huge in each of those. So some of them may be larger, some of them may be smaller. The way the philosophy that we have is vector architectures could be seen as providing the last level of that concurrency being actually implemented or supported by hardware, by the way, not by software. And being, I don't know how many vector lanes you have in your vector architecture. I would kind of differentiate this kind of structure from, for example, if you have I don't know, GPUs, okay, where you have a single level that does a huge amount of parallelism to many threads. Probably you don't have those many of those into a node, but the GPU has many threads which then map into a limited set of resources. So what I try to say is we try to go through this a little bit more, I believe, a more balanced, more nested tasking type of structure, which, by the way, the lowest levels, but what we choose in RISC-V, this last level would be RISC-V vectors. And one of the features, I mean, you have also today ARM, which has vector SVE, which has vector architecture, but we decided to go for a vector architecture which is relatively large, 256 element vectors, okay? Probably one difference compared to other vector architectures, there are some, so you have NEC, for example, is that we have only 8 lanes per core, which means actually every instruction is 32 cycles to implement. And so this is kind of going to a balanced hierarchy where every level, I think, and we try to go to a level which at this lowest level is not a huge number of levels. Of course, at the end it will be large, but you can put 8 lanes, you could put 16. So these are the discussions about the dimensioning, but it's a relatively large number of lanes, okay? Second idea is about this asynchrony and this latency to throughput evolution, which we consider as being of task-based models. And we did work a lot on these task-based models and pushing those contributions into OpenMP. I think this is a place where this asynchrony and overlap can be achieved. I think this has to go also and also affects the interaction and the composability of OpenMP with the levels above, with MPI. Even the same concepts in this kind of unifying theory, same concept can be applied at the level of computational workflows. And we have been working on a PyCon, something that parallelizes Python work and spawns tasks out of sequential Python code. But in reality, going down to the architecture level, if you look at RISC-V with this long vectors philosophy that we are trying to push, in reality is also a little bit of that. You can think that actually every instruction is just like a task, okay? And in reality, OMS or MP superscalar, all this activity that we did in the past at the level of runtimes and OpenMP programming actually leverages the name from what the architects have been doing in the past on out of order execution. So in a sense, the comment is that this layer interface, this layer here, has this ability to keep having underneath a concept of task and asynchronous execution, only that their order and their possible executions order are controlled by hardware rather than by the runtime. But the philosophy is kind of about the same from the very low level to the very high level. This is an idea that we think that this design decision of long vectors, RISC-V long vectors, is kind of pushing. There's another concept which I consider very important, is this need of coordinated schedulings between levels. Typically, the current practice is there's very, very limited coordination across levels. And at the software level, we've been working on things like what if a given program, MPI program, at a given point in time does not have OpenMP parallelism, would it be possible to leverage those cores that are idle by another process in order to holistically keep all resources active, sometimes working for one process, sometimes working from the other, but all the resources in one node being active? This is kind of the idea that how we apply this idea at the level of runtime interaction between at the OpenMP level, MPI OpenMP level. But if you think of the feature of vector length agnostic of RISC-V, which, by the way, vector also SVE in ARM is vector length agnostic. I think that they have one nice feature, one nice thing that actually matches relatively well with this idea of coordinating layers. And this is kind of this osmotic membrane at the ISA level, where essentially the program on top says what I would like to use, and it's a decision of the architecture itself to say, well, you would like to use that, but you have to use this much. For example, in RISC-V, this is with the VZVL instruction, where you tell I would like to use a vector of length 100,000, and the hardware can tell you, sorry, I cannot handle 100,000 in a single instruction, but I can handle 256. So the upper level can adapt to 256 and will iterate, of course, but will adapt in a way which is actually independent. The source code is independent of the actual architectural vector length. And this is something which I think is interesting, is being exploited, and probably has been pushed sometimes for reasons like code size or things like that. But I think it opens a huge set of opportunities in the same way as, so it's a negotiation between software and architecture about the amount of resources to be devoted to a given part of an algorithm, and dynamically just to a part of an algorithm. So I think this has huge set of potentials, and we have only been looking at scratching the very, very, very initial surface of these features, and provides a clean kind of this osmotic type of interface, which is a clean and elegant interface to decouple those two things. Finally, the other fundamental philosophical idea is then what I said at the beginning about the applications. What do application programmers need? And I really think they need that we offer them kind of homogenized interfaces, homogenized architectures, that they underneath the machine will be as heterogeneous as needed and will have different, but trying to provide an interface which is really as homogeneous as possible in order to just to get programmers survive the transition. And in our case, particularly, we believe this happens with, we handle it with, as we said, with this nested OpenMP stuff. But for example, even within OpenMP, and you see I'm pushing a lot for OpenMP, but personally, there are also things that I don't like in OpenMP. And one of the ones that I don't like is this fact that you can do target offload, you can offload code to a device, but when you are on the device, you happen to have a kind of a different set of directives. Instead of the classical tasks and work sharings, you have a kind of accelerator specific kind of directives. And we believe that in our approach, it should, one thing is that you may want to offload to a different kind of device, but the programmer's view on the left side, on the host side, and on the offloaded side should be pretty similar. And in a way, for example, this vector length agnosticism that we mentioned before here is also yet another way of supporting heterogeneity. Maybe not not heterogeneity in terms of functionality, but in terms of performance. Yes, one can have something equivalent to the big little cores, okay, where you may have the same even in a single system, the same source code may go through a device, which here tells you I can execute vectors of 256, and the other device can tell you I can execute vectors of 175. So this flexibility is something that homogenizes and would help a lot systems software at all levels, I believe. Just finally, the thought that this has to be kind of all of these visions and ideas have to really be then based and sustained on very detailed measurements, as I mentioned before. I will comment a little bit more on that. So probably this was a long discussion of some of the philosophical aspects. Hope I have given a little bit the perception of some of the fundamental principles, and I will try to explain now a little bit the history of EPI, and I will try to see how these generic visions from my specific point of view have been reflected in the EPI project. And EPI was a European project, was set up as an FPA, which was a kind of large consortium to try to develop components, which actually the objective was low power microprocessor technologies, which could be used to solve everything, right? And probably this is always something we have a little bit this willingness to fix everything. I try to represent in this cartoon where I just change a little bit the original Spanish text by something, but it's a little bit like that. We try to address everything, and what has been the result? The result is instead of developing these low power microprocessor technologies, there were actually two proposals. Some things were ARM based, some things were RISC-V based. As we push for this RISC-V approach, as I mentioned, with this. For some of the fundamental reasons that I have explained before, RISC-V was not seen as a totally really available and ecosystem and infrastructure for certainly for HPC. So there was a kind of initially safer status of leveraging and licensing ARM-based technology. So the project has actually had these three streams. Actually, these two streams, which this one was the leveraging ARM SVE and trying to integrate several of those cores into a chip, put into the chip or do experimental initial design from this is actually leveraging licensing technologies. It's nothing more than integrating it. Here, the idea was to start developing from scratch full EU designs from full IP owned by the partners, and you'll see there's a bunch of partners, each of those contributing different components. And actually there was kind of an architecture like generating kind of a grid of tiles. Most of the tiles would be ARM tiles from ARM, like integrated there. And they would be doing some exploratory tiles, a few of those, very few, with using this RISC-V based acceleration technology, which we call the EPI, European Processor Accelerator. This was kind of the structure of the project, the design. There were some other components. At the end, the situation is that the two things are not yet integrated into a single chip, but I will be focusing on this EPAC, but maybe some of the aspects will have to be considered that this is going to be RISC-V, but it was initially thought to be integrated or plugged into this ARM kind of generic infrastructure. Even, and I have to say this also, even within EPAC, there are kind of two or three different visions of topics of areas of research for this development from scratch. There were some specific devices for AI acceleration or stencil computations. There's this RISC-V vector. These are the partners involved or mostly involved, interested in that, and there has been a cooperation between all of those. So this is the team on the RISC-V vector extension, which is what I will be mostly presenting afterwards. And there's also activity on things like even if today people goes to reducing precision, for some cases there's also a need for extended precision. Okay, so these are kind of efforts that have been integrated into the design. I will show. But just here, I'm kind of repeating a little bit the kind of vision and the kind of philosophical considerations that were done in this RISC-V vector acceleration. This thing of long vectors, with the idea that long vectors is less work, more rock. More computation with less work. The opportunity to convey information to the lower level. A single instruction conveys a lot of information to the architecture. The possibility of the coupling the front end and the back end. This is something, I don't know, I always look at these images of these small birds in the nest, and they all of them with their mouths open, and the poor mother going out, getting an insect and feeding one of them, and the mother does nothing more than going and trying to feed the insects, and the birds are always with a mouth like this. And that's how I see very often the processor designs. When you have a front end which every instruction takes one cycle to execute, in the back end, the front end goes like crazy. I wouldn't like to be myself in my future life. I wouldn't like to be the front end of an Intel or of an ARM SVE, I don't know, because it's always having to run some all the if you take a branch misprediction, or you are actually suffering. So the idea here is that to decouple these two kind of things. So this is kind of the fundamental, I would say, the fundamental characteristic of the architecture, which initially was kind of structured. The original was say, okay, we're going to have these specific accelerators, which would be actually a specific accelerators handled typically like any other accelerator. It's just a memory map device with some control registers where you say from here to here you have to operate, and but handled by the main scalar processor as an I/O device. To this vector extending the vector capability of the scalar processor with a device, a vector lanes, which in a sense is what I said before, act like you have the scalar processor, and it's like homogenizing the heterogeneity, moving the devices which end up having the high-end computing capability, you move them under the ISA of this scalar core. Okay, and it's kind of, from my point of view, it's kind of homogenizing the heterogeneity. So now, from now on, programming this device is using the traditional load, store instructions, add, multiply, using the traditional compiler techniques, using everything. You don't need to do, in order to, you can leverage a lot of work, a lot of intelligence from that has been put in many of the open source infrastructures around. There was also another question here. Initially, we had an L1, we had an L2, we had an L3, and all of this was going to be in one of those tiles that would be here connected to the ARM thing. And there was also this decision of, what do you put? If you would put a chip for HPC, you want to put a lot of floating point units. If you want to put, so what do? You put a lot of floating point units, or you put a lot of memory? And what is the trade-off? What is the balance? What is the right point of what is being put or not? And at the end, this initial architecture, which had these many levels of cache in the hierarchy, and which was intended to be put in one of these tiles in the generic mesh. So you would actually have an additional last level cache, let's say at the overall ARM kind of infrastructure level. So the accelerator tile, which we were designing, would be right here. So we ended up deciding to reduce the amount of memory put into the device and putting a little bit more of compute. And this was kind of the kind of architecture in a very abstract way, which is a NOC, which connects architecturally, let's say, up to 8 of these vector processors, which have their scalar and vector unit, up to 8 of these additional accelerators for the stencils or for the AI. All of those connected through 8 cache banks, shared cache banks. Okay, so there's a small local private cache here, but very small and only used by the scalar core, not by the vector core. And there's a shared cache out here, which is also not huge. So some of the criteria here, the processor here, this actual scalar core is simple, it's a two-way in order. This thing was leveraged coming out from the Ariane core from ETH. And so it was moved to way out of order. So we had this decoupled BPU that I mentioned before, 8 lanes to 56 vector elements, so 32 cycles per instruction, per arithmetic instruction. One of the features of this scalar core was very large number of MSHers. It's to actually enable this throughput-oriented thing, throughput with memory. It's being able to have a lot of in-flight memory requests, which actually happen to be fed or provided, because if for a scalar processor providing such a huge number of in-flight memory requests, you need to decode and fetch and decode and execute a lot of memory instructions. So in here, the long vectors is kind of an enabler. One instruction instantiates a huge number of memory requests. The L1 is coherent. The L1 in these sockets is coherent, and well, one other characteristic or dimension is the bandwidth here. The bandwidth entry and bandwidth for each vector core is things in the order of 1 line per cycle. So full line, 64 bytes per cycle. It's relatively high, certainly much higher than what it is or what it was on the original Ariane core. I will show some numbers maybe afterwards, but it's a relatively high bandwidth. And these caches were not that large. Okay, it's half a quarter of a megabyte each. And the other thing is, the idea is to have cache allocation control mechanisms to let a little bit the programmer steer a little bit this communication between layers, let the programmer steer, hint the architecture. If the hint is correct, the behavior, the performance, you may gain performance. If the hint is incorrect, it's only a hint. You will only suffer in terms of performance, not in terms of the algorithm not working. So the result was this Avispado core, which is the scalar core in here. So it's the Avispado, which is just extending the Ariane thing. So there have been work by Semidynamics, it's a small company here in Barcelona. They have been doing changes in the typical architectural things to try and improve while still being a two-way in order core from this part of the scalar part. They have spent a lot of effort in this memory interface unit, let's say, where of course they have their local cache for the core, but they have this ability to really issue a huge number. This up to now in the current version is up to 128 MSHR, so a huge number of in-flight requests toward the memory. Of course, these in-flight memory requests are not fed, in reality, not provided by the scalar core because it's unable, but they are fed by the vector lane, by the vector lanes, which is a vector unit. It's like an additional functional unit, which is a vector lane, which is actually executing the vector instructions. And the whole thing is under this single RISC-V ISA, the standard ISA. We actually had at the beginning, we have a V07 standard. It was not yet fully defined. Now we have a standard 1. So the actual implementation that we have here is for V07. We are actually extending for the next versions towards V1. So this is on the let's say the core part. If we go to the inside here, this is the vector processing unit, which happens to be, in a sense, happens to be a processor in itself. I would like to think of it as a punch tape processor, which essentially receives the instructions from a punch. Well, the punch in this case happens to be just the interface between the scalar core and the vector core. The scalar core sends the instructions, and the guy has the standard kind of things. And there's this discussion: if you have long vectors, do you need and each instruction is 32 cycles? Do you need reordering? Do you need a little bit of out of order? And our philosophy was moderately yes. Okay. This offloaded task, you can also see as a way of offloading tasks from this general purpose core to this integrated inside it vector accelerator, integrated under this ISA. And based on this feature of this long vector lengths compared to the number of lanes, but you can really leverage a little bit of out of order. So we do have here a unit which decodes the instructions, kind of implements the standard out of order execution things with limited out of order, but does a little bit of renaming. We have architecturally 32 registers, physically 40 is, we believe, enough. And this is reordered with the possibility of actually getting to achieve concurrency between three major resources that we have in here. So we have a major, which is the load store unit, which actually, is the interface is actually residing on the scalar core. The functional units here, which is these 8 lanes, this bunch of functional units, and also the shuffling infrastructure. Also, there might be need to communicate between there are shift instructions, there are rotate instructions, or beer gather instructions where you communicate data inside the lanes. Other design considerations that you might consider probably even strange is kind of 5 banks per lane here. 5 banks, the registers are split in 5 banks. And by the way, they are single ported, which is probably not very normal design decision for many architectures or many systems. But that was the choice, trying to minimize the area here and try to enable sufficient bandwidth for keeping the whole thing, again, with the throughput orientation, keep the whole thing, enable the whole thing to keep active every single cycle. And the data shuffling is a bidirectional, well, it's not a switchable bidirectional ring, okay? This has been presented at the RISC-V summit this year. With those characteristics, essentially the architecture, let's say there was a test chip, which was designed. This test chip had included 4 of these, so there was the NOC. The NOC, by the way, is just a standard SMS, 2D mesh, and with the typical dimension order routing schemes, the typical stuff. Each of these things is 64 bytes per cycle, so it's relatively high bandwidth. And you have, every node has the Avispado core plus a home node, one of the catch nodes. There are 4 of those. There we have the stencil accelerator for the AI and the stencil computation. We have the standard precision processor, and we have a bridge for an external FPGA. So this is just a test chip. It's not a real standalone self chip. So a lot of the memory controllers and all of these things here, you have shared sufficient bandwidth here, but a lot of the logic is of the controllers and Ethernet controllers and all that is externally. So this is what was implemented, and this was implemented in a chip, which is more or less this size. It has these 4 vector processors, and it has these extensile accelerators and the connectivity to the external FPGA. So this is a little bit more of detail on the processor side. You see the cache, the shared cache banks. You see the individual register banks. We have a relatively large register bank, which philosophically also implies that this trend towards moving locality control down, one level down. Okay, but I think I believe it's kind of reasonable. It's kind of leveraging also the compiler capabilities of using that level of locality, and that was the design. So the chip is there, that the chip is back, so something like this. And we started the bring up process. Actually, it was possible to run some tiny shell, run some vector code at 1 gigahertz. At the end, it comes out that it's not fully functional. So there were some issues in the design, so there's not fully functional, but it's still possible to run on the 4 vector cores. It's possible to run small vector codes. And so we are actually going to have a new tape out probably, and we are in the freeze for the new tape out will be in a few days. And by middle of the year, we'll have this new tape out. Just in the first signals of life, the first word of the guy was curious. It was interesting. You run an XP program, and you measure how long it takes. You run the vector version, the scalar version, and the vector version, and you see there's a difference of 25x. Where you say, well, I only have 8x FPUs, right? But it's true that you can say, okay, this is the benefits of long vectors because I don't have to decode as many instructions and I can execute the floating point units back to back. There's other things you also have. It's true that, as I said, we have a much wider, much broader load store unit. Okay, so the thing is where you put your resources in the architecture, and this ratio of 20-25, we'll say it is a kind of a ratio that we are really seeing very often for some algorithms. Anyhow, this is on the test chip. The thing is, what about software development? What about really exploring and because one chip is this thing that you say. I mean, if there's a mistake, you have to wait for 6 months, 1 year, or more to get something else. So, what did we have in terms of software development infrastructure and actually verification infrastructure, large-scale verification infrastructure? We have what we call software development vehicles, of which one of them is just a software emulator, which means You have your source code in C, C++. You compile it with the LLVM, compiles, generates RISC-V vector code, and you will run the RISC-V vector code on a scalar RISC-V core, from commercial scalar RISC-V core, with an emulation library that emulates the vector instructions. And what we end up having here is we generate traces that describe the sequences of instructions, the sequences of memory addresses used by those instructions. So we can visualize that with the standard analysis tools that we have at VSC. And we can really additionally include simple simulators that end up reconstructing timing, providing timing information about what would be the cache miss ratios given a certain cache size, what would be the importance or the benefits of a given cache management policy or these cache allocation mechanisms that I've mentioned, or actually not only cache, because it can be about what is the amount of reordering that you support in the vector lane. So what kind of the reorder buffer size that you support there. So this is the kind of infrastructure that we have, which we consider is the first step for people to really try some programs in RISC-V vector and try to estimate whether the program looks good or bad, or what would be the estimate potential performance of that. This is something which is available here and can be executed in QEMU. It's probably a bit too slow, but it can be executed on a scalar RISC-V cores, and that's really, I think, really nice. At least for us, to me, it has been a good software development infrastructure as a first initial step, and lets you get a lot of insight. And we have applied it to many different configurations and tried where we can visualize things like for every this here we have these timelines where this the individual instructions, and we see in this one the vertical dimension is the instruction timing, how many cycles every instruction takes, and the coloring is the type of instruction. Or you can look at the memory access pattern, or you can look even at, for example, LRU stack distances to see what would be the impact of different cut sizes. You can certainly do the simulations and say what actually for different cut sizes or for different levels of latencies of the instructions, what would be the impact on performance. So this is a kind of infrastructure using this thing that we have used. We have used for the standard HPC applications or kernels, like the typical matrix multiplies, sparse matrix vector, the typical FFTs, but we have also applied to some of the AI kind of programs or applications, and where you see, their typical, well, the program counter structure, what's the memory address used, or LRU distances, and overall, this is nevertheless is just as a way of co-design towards the application developer. It's kind of recommending the application developer certain kind of things, or very typically things. You say, hey guy, you have and you see that you have an algorithm without knowing what the source code. You have an algorithm that does is doing too many, has quadratic, so cubic computation, quadratic data, and what I see in the instruction set is cubic computation, cubic data. There's something wrong. So this kind of very simple fundamental things, but end up being good productive information for the application developer. You tell him this is your locality, probably you could improve it, or this is your register usage, and out of the 32 registers you are only using 8 or 6 or 2. Maybe you might benefit from unrolling. So there are these kind of recommendations that you can do. Applications in geophysics, the typical stencils, and you can end up having information, for example, of memory addresses. What are the memories? And you see this kind of stride one accesses to different vectors. This is what we see here. The coloring depends on the pitch. Sometimes it's the instruction, sometimes is for example whether those accesses are hits or misses. For example, this is which of those are stores, this is which of those are hits and which of those are misses. So you really get a feeling on which data structures you get more failures, on which you also get a feeling of what's the evolution of the IPC throughout. So less IPC here, more IPC here throughout the execution. So it's the kind of information that we get. We have applied it to an application, for example, mimicking the typical radar systems in automotive, in cars for autonomous driving. So, and it has been very useful to, for example, to improve a lot of our compiler, to say we have to put more emphasis on the handling on the compiler of complex data. We can do optimizations to convert indexed accesses generated by the compiler to strided accesses, or we have to increase the reuse through registers, or very typical thing sometimes because people start getting architectures with LLVM, start getting architectures which have a very small instruction vector length. They have put the optimizations like, oh, if I have 2 instructions or 3 instructions, one after the other, which actually I know that it could be converted into a vector length instruction of vector length 3. Maybe in an AVX, that's a significant fraction of the percentage. In our case, is not. So there are things here where even if you share the infrastructure, the actual decisions, what is best for a given architecture, the decisions change. So this is what we use to steer a little bit the compiler optimizations. And this is what we have in terms of the compiler. We have the compiler which supports 0.7. We have the compiler which supports 1.0. And you can program with intrinsics, which more or less correspond to individually to one instruction, more or less, because the compiler, even if writing here, the compiler can even actually reorder, can actually do spill code generation, can actually do invariant extraction, can do. So it's still programming vector code, but the programmer can even, the compiler can even optimize. Or you can use pragmas, the typical either Clang pragmas or OpenMP pragmas like the OpenMP SIMD. And that brings your architecture, your application to execute the vector code. We are in this process. Of course, the compiler is certainly not perfect, but is sufficient, I think, for doing a lot of experiments. I had this slide was at some point in the time. So I mentioned that we were having ARM and RISC-V, all of them together initially in the target of the design. Now, and I said now there's actually a big delay in the implementation of the ARM chip, and these things are underway licensing discussions, and it's not going to be integrated there. But in reality, we did develop another software development vehicle, which was actually merging in FPGAs and hard cores, ARM hard cores with RISC-V cores, being able to install and to boot Linux on both sides, and being able to work and develop the OpenMP offloading runtime, so that you could start your OpenMP program in the ARM and offload to the RISC-V, but you could even offload from the RISC-V to the ARM. And you could use that, in that case, you could consider the ARM as an accelerator for I/O, for example, and you could have your RISC-V as the basic self-hosted kind of system. Okay, so this is something that was done. This is done by Ford. They have been doing very good work on several of these things. So, and this is kind of an infrastructure that we have at VSC, which where there's been a lot of the integration of between, certainly in this case, Ford, VSC, and Semidynamics. We have a rack where we have clusters. So some nodes are just blades with commercial RISC-V cores, each of them 4 cores, standard Sci5 cores. Okay, we have some of those, and what we have done certainly is we have deployed the SLORM, we have deployed MPI, OpenMP, we have deployed our VSC performance analysis tools there. But we have also deployed this RISC-V vector emulator that I mentioned before. So one can do the software development, and all the process that I explained before can be done on these systems from home, let's say, but just remote logging into the system, allocating a node, and doing all these operations here. So this is one of the things that we have in terms of enabling RISC-V vector development, and we have here the compilers, the cross compiler. Well, not the cross compilers, it's RISC-V vector compiler. So we have here 3 nodes, which in reality are 3 FPGAs, 3 relatively large FPGAs boards. And on each of these FPGA, we have put a subset of the test chip, a subset of the RISC-V core. Essentially, we have put only one Avispado core, one core with its 8 lanes. And we have put 4 memory banks, and we have put the cache, the crossbar, the connectivity, the crossbar. We have put externally some things like Ethernet adapters. We have put UART. We have put external memory controllers. So essentially what we have here is a system which essentially boots Linux. And here you can run the the vectorized codes, and this executes native vector instructions, the native B07 instructions. So you can run, compile the bug and check that the thing is right on this course, and then on the SDB, on the software SDB, and you can then run on the real hardware one. So this is integrated as in a CI framework where actually when we detect things, issues that we certainly detect, so people can update the RTL, fixes the bugs, and nightly, let's say, there is a rebuild of the image of the bit stream for this device, and we can keep updating the design kind of on a daily, weekly basis. And as I said, this is kind of accessing through Ethernet. So there you can do other things like you can compile on these ones, you can store through NFS on the file system, and you can load from these other ones. So this is just a cluster for doing this development and for doing this evaluation. Just a little bit of comment of that was the whole chip. It actually had a few more things here. This is what has been put in the FPGA. So only one core, 4 memory nodes, the NOC, and actually an external memory controller. And on which you can really measure and play and obtain waveforms of the behavior of the different things, and try to experiment with different characteristics of the architecture. You try to see the I don't know, the protocol, the CHI protocol. You try to look at, sometimes you expect the whole thing to be perfectly pipelined, and you start seeing bubbles injected in between, and so not achieving the full efficiency. And then you try to find out what is it, and then you essentially end up adapting and correcting the RTL and adapting, avoiding those peaks. So what else can we do? We can really run on this cluster. We can really run the full, so some kernels, and run them, and actually compare them, run them in other architectures that we have a PSC, and we can kind of compare the efficiencies of the performances. Or, I mean, ISO frequency is easy. I mean, you know the frequency of the cores, and by the way, our FPGA is at 50 megahertz. Okay, so it's not, but it's fair. It's sufficient. You could try to make estimates of power or area or cost. So those are more I don't know, it's real, very rough estimates, but it's an interesting kind of study. And then you try to identify what to improve in the architecture, as we have said. So we have done some of these philosophical considerations of, if you compare to other architectures, and what I want to say here is we are comparing the SDB with things like NEC Aurora, for example, the Fujitsu ARM, or the Mare Nostrum, the Skylake. And it's interesting to look at the different philosophical decisions in terms of amount of sizes at the different, if you look at an abstract model of the architecture, amount of sizes of register banks, amount of the amount of state in L1, the amount of state in L2 or L3. It's a kind of interesting, and I have not put here, it's even more interesting in terms of bandwidth, for example. But we are doing this kind of experiments, and we are reporting, for example, the typical kind of stream-like benchmarks. We are kind of doing loads or just stores or the copies, and we can compare to our scalar execution, the vector to the scalar, which we see this factor of 30 times is relatively frequent. We can compare to other machines. So this is compared to Mare Nostrum, for example, in terms of the bytes per flop achieved, depending on the size, the size of the problem. We can compare to NEC vector, and you see NEC is really a beast in terms of compared to this. But compared to the Skylake, is really competitive without, I mean, it's kind of been a poor man's design. I mean, we have been starting from scratch. We have been doing it with the Global Foundries 22 nanometers. So it's kind of, but it's interesting kinds of insights. Or, I mean, we have tried different versions, for example, of the AXP code. This is AXPs with different levels of unrolling and different levels. And it's curious. And this is the actual speed up compared to a reference case, the same reference case for all of those. And we have, for example, that the FPGA at 50 megahertz for this AXP, in these cases, is actually faster than the ASIC at 1 gigahertz. Okay, the scalar ASIC at 1 gigahertz. So is an interesting type of resource that essentially to us is kind of gives us certain kind of evidences that there are potentials in this long vector type of approach. We compared, as we said, to the NEC or Mare Nostrum on ARM. We compare AXP, and essentially, if you look at the ratio of the bandwidth of the performance that you achieve between those, sometimes you correlate that, and it's totally directly correlated to the memory bandwidth supported by the device. Sometimes you end up computing efficiencies, which would be these ratios or kind of ratios between the performance and what should be the peak for the given device. And sometimes we see that we get nice efficiencies in terms of the usage of the resources, which was one of the objectives of the processor design. Okay, so we have compared with the sparse matrix vector, comparing with MKL, with the NEC library, and you see some of these behaviors or competitiveness in terms of this is flops per cycle. Okay, this is really, but in this kind of metric, this kind of give us indications that we believe this is actually useful information, and useful information for co-design. If you look at this difference, you can argue and justify what it is, and there's insight. We have to improve, yes, if we want to get something closer to the NEC. Is it possible to get closer to the NEC with the other constraints of performance, of cost, and being it's very arguable, but you get a lot of insight. Or FFTs, for example, you have FFTs in terms of absolute flops per cycle for the FFTs, or in terms of efficiency of those FFTs. And it's curious that we have here, this green one has even better efficiency than the other architectures. So we are in this process. Also, but playing with the different, we look at if there is a problem in the architecture, we try to change the RTL, but if it's a problem in the compiler or the instruction can be improved, the instruction scheduling of the compiler, we try to modify the instruction scheduler, and we can go from these flops per cycle to this flop per cycle with the compiler refactor with the optimization implemented on the compiler. Manually, you can get a little bit better, but it's probably worthless. And we have some curious, strange experiments or experiences on taking, when this is an astrophysics code, you take it, you run it, and in terms of iterations per normalize again, as if all of them were at the same frequency. It's kind of competitive with other processors, some of those. And in reality, you end up finding that for some of the data sets or some of the algorithmic setups, it's even actually worse. And I mean, it's not a matter of saying we are good or we are bad. In this case, we just found that it was something like related to a compiler vectorization stuff. So everybody else can do it also. Okay, so it's the kind of insight that kind of this holistic co-design approach and possibility, and I think it's a lack that we have, that we can touch the different levels of the architecture. Is a very, very interesting experience to push into that whole architectural design, a little bit this holistic throughput view. And so I like to finish, so you have access here to the public, to the infrastructure. If you want to use it, I like to use this example of Sagrada. This is Sagrada Familia when I came to Barcelona, which had only 4 towers and nothing else, nothing around. And this was a decision when they got funding they had an important funding. They had the choice of raising 4 towers to the top or raising everything 4 or 5 meters. And they decided to raise just 4 towers to the top, because that was actually giving the opportunity to see that there was something special behind it. And that's what made it possible to get the continuing support and the tourists to actually get to where we are now. That had it not been for COVID, they would have finished in 2026, I think. With COVID, it might take a little bit longer. Anyhow, this is the general presentation. Is a little bit of philosophical point of view, a little bit of numbers. If you have questions, I can try to expand, or I can try to discuss a little bit more.
Thank you very much. It was exciting. I think that a few people has a question there. I think that most of them were from Ran Ginosar, so maybe I'll try to open his mic first, and then there are two other people who had questions. Just a minute. Ran. Okay, Ran, I think that right now you can.
So Alona Mead had the first question, and I think it's more important. Can you start with Alon maybe?
Sorry?
I'm saying, I told Avi.
Okay.
There was Alona Mead asking the first question. Maybe you can ask Alon and then Sharon to do their questions first.
Okay, so I'll try to find with Sharam. Are you still just a minute? Can you ask your question?
Is this question on the chat about the vector-length agnosticism?
These are the questions on the Q&A.
So about the vector-length agnosticism, I think, and is it possible to avoid the specific kernels? I think it is very highly desirable to avoid. So one thing is, in the same way that nothing is perfect, nothing is perfectly clean. So there's this saying, if how is it said, if good guys go to heaven, bad guys go everywhere, right? You can if you have something which is not perfectly elegant, you can really do certain things. But I would personally recommend not to, and I would personally recommend to try to think or use on the fundamentals and stay. And this was one of the things in the initial slide. Stay elegant. Probably the vector length agnosticism is something where we have not had sufficient experience, whether both ARM and both RISC-V. We are introducing that. It's not sufficient experience. I said it. I think it has a huge opportunity to really come out with a lot of malleability, a lot of adaptability, and dynamic kind of practices. I think probably we have to gain much more experience. The very greedy type of approach of trying to say, oh, now I'm going to use this very specific thing, which gives me 2%, 5% more performance, I think we should try to avoid. I don't know if I answered the question, but so OpenMP is not perfect either. Do I argue that I'm argue for OpenMP? If I see one of my students to use the thread private clause, he doesn't pass, okay? It's as simple as that. A lot of people, or some people has been obtaining from the thread private clause, has been obtaining performance, yes. But this is bread for today, hunger for tomorrow. And that's kind of my perception or my position. Does that make sense or not?
There's another follow-up question. Can you see on the chat about the libraries?
Libraries and BLIS. Yes, we have compiled BLAS, and there's a team of people who was, one of them was actually the implementer of BLIS, and he has been using the infrastructure and has been actually changing BLIS, this thing of what you say of the flock size, and has been changing totally. So not so it says, I think as far as I know, most of what he does is still not using totally the vector length agnostic thing. One thing is that the vector length, you being able and being forced to. He has been adapting it, and he has been adapting it with the vision of more than anything of leveraging the long vectors. And this changes a little bit the kind of blocking structures that BLIS has compared to the traditional architecture, which is register blocking and L1 catch blocking and L2 catch blocking. Okay, so it changes a little bit, but they have been doing it, and I believe it's really, really nice. It will be available. Yeah. So does that imply a little bit of change in the programs or in some of the programs? Yes, it's a little bit of change. It's a change that is still, from my point of view, very productive, very clean, very elegant in terms of the way it is done. It's just changing the block sizes. Typically, you have very tall and thin matrices, and for some cases, they go to thin and wide. I don't know, but it's just changing the values. What leverages then the ability of the, for example, this thing of moving locality to the register, to the level 1, to the registers is an important thing.
Can I ask my question, because I have to leave for another meeting in about 10 minutes? Yeah. So I actually had two questions. Question part one is, who's fabricating the ARM tiles for you? And the second question is, you mentioned a lot of applications, but have you tried to run LinPack? And I'd like to know if you can share some LinPack numbers. I know it might be preliminary, but I want to get a feel for that.
Okay,
thank you.
So we have tried to run LinPack. We ran LinPack on the core. For this LinPack, we were using Bliss, right? And the Bliss version, the work that the people had been doing on Bliss didn't have the TRSM routine vectorized, okay? The result was that it was a lot of scalar code, and then yes, the DGEMs were vectorized, but the TRSMs were not. So we are in this process, yes. So we run LinPack. Still, I cannot give you numbers. I mean, we can give you numbers, and we can give you numbers for what I told you for these DGEMs, which is the typical 90% of the peak. That's the typical thing. And still, we have issues there because of, I remember, these five register banks, and there are issues there that can be improved. But it's 90% is like a standard processor. The other thing you asked was on the who does the
ARM cores.
The ARM cores. So the ARM cores, initially there was Bull Atos, but Bull Atos is a system integrator, is not a chip. So they actually, there was a small company out of a spin-off of some of the people who was hired by Atos, who actually, the company is called Cyperl, and they are actually the ones who are licensing from ARM and are doing the chip, although it is still not yet taped out, okay? But it's a French company. Well, it has people in France, in Germany. It's Cyperl.
Okay, thank you.
And Ryan, do you like to ask your questions?
So the first, thank you. The first question is, you've shown a little chip with 4 microvector units together comprising a vector accelerator of 1 CPU. And my question is, how's the work split between them? Do they execute the same single vector instruction or 4 different ones in a 4-way issue type? And is this exposed to the ISA level or not?
No, the ISA level, so where will we have that? At the ISA, so you have 8 lanes here.
Yeah.
8 lanes here, but they are at the ISA level are under this thing, and this is like a single vector instruction. So each of these lanes has 1/8 of the register bank, and that's 1 operation per cycle, but it's the same instruction. There is some level of independence between the lanes. That's also interesting, which is when, I mean, if one of them finishes 1 instruction, it can start a little bit ahead of time the next instruction. There's a little bit of that, but it's just 1 instruction. Conceptually, essentially, is 1 instruction at a time. So the order between instructions can be changed, but it's 1 at a time.
And you have the a scheduler to split the work among the lanes, or is it automatic, or how is that?
Yes, this is the hardware, the execution of the instruction. If the instruction says operate this 256 element with this other 256 element, the hardware, the control automatas here, the control processor here,
Yeah.
Essentially, the automatas here, just everybody knows which part of the instruction is available to them, and everybody executes its part of the instruction.
Good. So if going up to the system level of the EPAC system, you've shown, I believe, 8 CPUs and 8 L2 blocks over a single network on chip. So are all the, yeah, that's the picture. So all these vector units and processors, are they all limited to executing vector instructions off L2, or can they also overflow outside to an external memory or DRAM somewhere?
They go through L2. So what they do here is a standard instruction. They do load into a register, and of course the load will be checked in L2, and if the data is not there, the data will be brought from the other side and will be maybe stored in L2, maybe not, but the data will be brought. The interface is the standard RISC-V, the standard load store interface. I don't know if this was the question.
Yeah, it's very good. Now, do you find the network on chip to create a bottleneck if all processors access all L2 blocks at the same time? Do you see network on chip crashing or slowing things down?
So this is one of the parts that we have only done simulation things, very short-term, very small simulation things compared to SDB, which you can keep running for 1 day at 50 megahertz, compared to a simulation which is much slower. So in what we have done, so we have not really done very extensive analysis of that on certainly on the FPGA, because we have only one core. We are working to put several FPGAs, but as of today we have only one core. So the answer is we have not done very extensive simulations. The other part of the answer is, nevertheless, in terms of as long as you kind of interleave the data, and as long as so there will be additional latencies, yes, but these additional latencies, the philosophy of the vision is that the long vectors essentially are a way or a mechanism to tolerate those additional latencies. So one of the things that we have and we are doing is on this. So there will be additional latencies in the implementations of the protocols here, because there will be contention in the messages here. One of the things that we have for that, and we don't have, as of today, we don't have very extensive experiments, but we do for that, is even that with one thread, that with one core, we are doing something like injecting dilation cycles here, right? We have a very simple IP to inject dilation cycles and say, if your DRAM, instead of taking this many cycles of latency, you put 10 more cycles or 20 more cycles or 40 more cycles. And the very, very few numbers that I have seen is a relatively fair tolerance to that in the performance of the processor.
Great. Now you said at the beginning that you are targeting low power by low voltage and low frequency, but at the end you show performance comparisons rather than any power comparisons to other implementations. Do you have any idea about or simulated results about power?
I mean, we have the numbers of simulated performance from the simulation, from the backend design simulations. We have power numbers from the actual, where is it in the test chip, from the actual operation, and we are actually doing those from the actual operation of the chip, where because we can put the 4 processors. We cannot put Linux, let's say, but we can put the 4 processors to execute code. And the idea, the measurements, I don't have something that I can really open, but I would say is relatively nice or interesting. And when I said low frequency and low voltage, was at some point in time we were using Global Foundries 22. There was the idea of using body biasing. There was also it's going to 1 gigahertz. It's not going higher, that you will have in many architectures. And actually, there are some people that want to go much higher. So it was this decision of what is a good operational point from that point of view. Of course, higher frequency is faster performance. So what is the good operational point? And what we targeted was this 1 gigahertz. So numbers.
Dan and Ron, sorry, Jesus and Ron, I think that people start to drop and maybe you can continue offline.
Sure, no problem. No, because you had also other. Sorry, I took too much time.
Because people start sending
I took too much
notice. So first of Randy, is it okay with you?
Yeah, sure. I'll get some more questions and get to his.
If
I'll send you the emails. And
you want to mail to me, yeah. If you want to mail to me, that's.
So first of all, thank you very much for the exciting talk.
Thanks a lot.
It was really, really exciting.